Analyzing the graphs of functions, part 3. We continue this very long process, and the first thing we want to do is ask ourselves, what should we be looking for in a graph? Now, you already have a fair idea since we've done a lot of this, but it's nice to organize it. First of all, with only algebra, here are some things you can find out about a curve. You can find out its x-intercepts. That's strictly algebraic. You can find out its y-intercepts. The x-intercepts being where it crosses the x-axis and the y-intercepts being where it crosses the y-axis. You can also check on its symmetries if that is of interest to you, strictly by algebra. Then as we move into the calculus, with our notions of limits, you can check for asymptotes. If you have rational functions, for example, or the trigonometric functions, you might be looking for asymptotes. You can also check end behavior. And what that means is check what happens as x approaches minus infinity or as x approaches infinity, and ask yourself what the function is doing. That would be done with limits. And finally, with our latest set of tools, the derivative, both the first and the second derivative, what can we find? Well, we can find out where the function is increasing or decreasing. We can find out where there are local extrema, and I'm putting it in this order because where it changes from increasing to decreasing is often where you have a local extrema or extremum. You can check where you have concave up or down, and then where the concavity changes, we have what we call inflection points. Now, as you proceed through this course and do more and more analysis of functions, you're going to want to have all these ideas straightforward in your mind and get a sense of how to do them, and do them probably in an order something like this. So you do the easiest things first and then do the things requiring the calculus later on. We'll continue from there. Let's look now at rational function graphs. Remember rational functions. They are functions f of x of the form p of x over q of x, where the p of x and the q of x are polynomials or polynomial functions with no common factors. That's going to make our arguments a little easier. So we'll say that these are polynomials with no common factors. And rather than write down the whole process here in general for a rational function, we'll do it by example, and I think you'll see better what we need to do. So let's take this example. Let y equal 2x squared minus 8 over x squared minus 16. And here's what we want to do. We want to find x-intercepts, and I'll write these in the order you probably want to do them. Y-intercepts, asymptotes, it's a rational function after all, where the function is increasing or decreasing, where it has local extrema, that's a max or mins, concavity, concave up or down, inflection points, and finally graph it. So this is really getting to be a thorough examination of functions like this. We're going to do lots of these, and they're good to practice. So let's look at this now. The first thing we want to do, let me rewrite the function, is to examine the form of the original function before I do anything else. If I'm going to be looking, for example, for x and y intercepts, it'd be nice to have this in as simple a form as I can get. So I notice I can factor things. On the top I can see that I can pull out a 2. That would leave me with x squared minus 4, which is the difference of two squares. That will factor 2. So I'll have 2 times x minus 2, x plus 2. On the bottom I already have the difference of two squares. So I have x minus 4 times x plus 4. Now that will make things a little easier for me. Also, right away, note that y is not going to be defined wherever the bottom goes to 0. So y is not defined, and this will come up again in just a moment, where x is equal to 4 or minus 4, which is what makes the denominator here 0. Let's continue on down our list of what we need to look for. The first thing is x-intercepts. And what I like to do is just remind myself x-intercepts, that's when y is equal to 0, because that tells me exactly what to do. I let y be 0 and ask myself, when could this expression be 0? Well, it can only be 0 if the top is 0, which tells me that x then equal 2 or minus 2 will give me y equals 0. Therefore, these are the x-intercepts. Y-intercepts, likewise, this is going to be when x is equal to 0. And if x is equal to 0, this is even easier. I just have to put x equals 0 in here. Let's see, I'll get y equals 2 times minus 2 times 2 on the top, and on the bottom minus 4 times 4 on the bottom. That all simplifies down to the number 1/2. Then I will move on to vertical asymptotes. And that will happen whenever the bottom goes to 0. And I already know when that happens. I've already indicated that's where the function's not defined. So those asymptotes, the vertical lines, will be x equal 4 and x equal minus 4. Those are two vertical lines. Finally, here under asymptotes, I will look at horizontal asymptotes. Now that requires that I take the limit of the function, and I'll do it in its first form, 2x squared minus 8 over x squared minus 16, as x goes to, well, either one of the infinities in this case. Because the x is squared, it doesn't matter which way I go. I'll get the same result in both directions, so that saves me one step. And from what I know about taking the limit of rational functions as the x's go to infinity, if the powers are the same, then I just get the coefficients of those two powers. So I get 2 over 1, which is just equal to 2. So that means I have a horizontal asymptote y equal 2, which is the line that the function approaches as x goes far to the right or far to the left. So before I do anything else, sometimes it's useful to have a halfway graph. So let's see what I've got here. Let me mark off a few points. I know that 2 and minus 2 are on the curve. Those are the x-intercepts. I know that if I mark off a point here that I call 1/2 on the y-axis, that point is on the curve because that's the y-intercept. I know there are vertical asymptotes at 4 and at minus 4, so I'll mark those. And I also know that if I come up here to 2, that the function is approaching this horizontal asymptote as I go out far enough in the two directions. So I don't know exactly what the function's doing out here, but this gives me a rough idea of where the function's graph ought to be. Now, to be more specific with this, I'll need to take the derivatives, so let's do that next. Y prime. All right, that's going to be the derivative, and here I'll write the function out so we'll all remember it. 2x squared minus 8 over x squared minus 16. And this is the easier of the forms that I had on the other page. The factored form was probably not the right one to use here for taking the derivative because it's going to be harder. It's with the product rule, for example. Here we do have to face the quotient rule, but it shouldn't be too hard. Let's see here. The bottom gets squared, so it's x squared minus 16 squared. Then we start the top with that bottom term, x squared minus 16, times the derivative of the top, which in this case is 4x, minus the top here, 2x squared minus 8, times the derivative of the bottom, which is just 2x. If I do some simplification here, and I can pull out, say, a 4x, and then I'll have some things to combine. I have 4x times x squared minus 16 minus x squared plus 4, it looks like. And on the bottom, that doesn't change, x squared minus 16 squared. And finally, this all nicely simplifies on the top because the two x squareds go away. And I get minus 48x over x squared minus 16 quantity squared. Here is my first derivative. I'll be using this. When is this first derivative 0? Well, it's 0 for x equals 0. And that's the only time this is 0. It's also undefined at 4 and minus 4, but then the original function had that problem too. It's just worth noting that we'll have to mark those places. All right, let's look at the second derivative while we're here. The second derivative is the derivative of whatever form I like. I think I'll use this last form, minus 48x, x squared minus 16 quantity squared. If I then apply the quotient rule to this function, the bottom becomes x squared minus 16 to the fourth power. Then I start off the top with the x squared minus 16 squared times minus 48, which is the derivative of the top, minus the top times the derivative of the bottom, which is 2x squared minus 16 times 2x. All good practice, I hope. And you see there's x squared minus 16 in a couple places here, so we can factor it out, at least one factor of it, one power of it, and that will cancel with one of these. And we'll end up with, after we clean this up a bit, I'll let you check the algebra, minus 48 times 3x squared plus 16 all over the bottom, which is now x squared minus 16 cubed, because we got rid of one of these factors. So here is our second derivative. It's always worthwhile to pause for a moment and notice what you can see. Look at this. This top is always positive. So the top is always positive. So again, when I'm checking positive and negative later on, I won't have to worry about this top. And I guess I should say the top is always positive with the negative sign in front of it, and that's not right, so it should just be positive. That ends up canceling out. The top is always positive, and the bottom, of course, will depend on what number you choose, because it's a cube here, and the cube will preserve negative signs. So this is always positive, so it is 0 for no x values. That's interesting. All right, I think we have enough information now to go ahead and assemble a picture here. Let us go ahead and write down our derivatives, minus 48x over x squared minus 16 squared. And then the second derivative, which is plus 48, don't want to get that minus sign in there, 3x squared plus 16 over x squared minus 16 cubed. Now there were three numbers that turned up. They were minus 4, 0, and 4. And for the first derivative, it was 0 and the plus and minus 4, that's where the function is not defined and the derivative is not defined. So all of those will have bearing for the first derivative, so let me mark all of those. For the second derivative, again, the 4 and minus 4 have bearing, but there's nothing on the top. So those are the only two that affect the second derivative. In the first derivative strip here, as I've done before, I will now pick numbers that are much below minus 4. Of course, that will make this negative times negative, which will be positive. So the first derivative is positive here. That means the original function is increasing, hence going up. Between minus 4 and 0, you can pick some easy number, but it doesn't matter. As it turns out, all that matters is what x is, and x is negative. So again, it's positive. So we've crossed over this line where we have an asymptote, and the function continues to increase. So it's increasing on both sides. Once we cross to the positive numbers, however, either here or here, this first derivative will be negative. So the first derivative is negative in both those regions. The function is therefore decreasing and going down in both of them. So the only place here where I have an increase and a decrease that would give me a local extremum is this one, and I have a local max as a result. Then if I look at the second derivative, which is here, remembering that this top is always positive, I only need to know what happens to the bottom's plus or minus sign. And if I'm below here, I've got a very high negative number. That squared is going to be a very large number. That will make that positive. So the second derivative positive, the function is concave up. It looks something like that. In the middle, I could pick 0, a nice easy number. That will make this positive, of course, on the top. And on the bottom, this will be negative. So this makes it a negative fraction. Y then is concave down and looks something like that. And then finally over here for a very large positive number, this is going to be very positive. And so y, the original function, is concave up and looks something like that. Now, you're tempted to look at these two places where the concavity changes and say, these are inflection points, but that would be wrong. What they are vertical asymptotes. And as vertical asymptotes, there is no value of the function there. So although they are changes of concavity, true, they are not points on the curve and so cannot be inflection points. In fact, therefore, there are no inflection points on this curve. Okay, time to look at the graph after we've done all of this work. Here's our original function, y equals 2x squared minus 8 over x squared minus 16. We could also, just as I'm passing this, since the x is squared here and in these positions, you might notice that this is what we've called previously an even function. If I replace x by minus x everywhere, it's going to still be the same function, which means it's symmetric across the y-axis. And you'll see what that looks like here. So based on all the information we got from the previous page and that little chart that we partially did earlier, remember we had the vertical asymptotes at minus 4 and 4. Here we had at 2 a horizontal asymptote. And we knew that the function passes through 1/2 on the y-axis, passes through minus 2 and 2 on the x-axis. And now we have enough information with the concavity to draw a picture in. It's concave down here in the middle, and then on the two sides it's concave up, and so we end up with this sort of a picture. It is asymptotic to the y equal 2 line eventually in both directions. It has these two vertical asymptotes. It has a local max here, and otherwise it doesn't have any local mins, and that seems to be everything we need to know about this. No inflection points again, even though it's concave down here and up here on either side, because there's no point of the curve on the asymptotic lines here. So I hope you enjoyed that. That should be the kind of function that you get a good set of experiences out of work. I want to note about rational functions before we leave them. Rational functions are not limited, although this may be all that you've ever seen, but they're not limited to vertical and horizontal asymptotes. They can have other sorts of asymptotes. Sometimes it's worthwhile finding them too. So rational functions can have other curves or other lines that are not vertical or horizontal, other curves as asymptotes. That usually is going to happen when in the rational function the degree of the top is strictly greater than the degree of the bottom. Now that didn't happen in our previous one. The degrees were the same, as you recall. But let me give you a couple of examples to show that just what can happen here. Suppose you have a function like this. F of x is x squared plus 1 over x. So the degree of the top is 2, the bottom is 1, strictly greater than the bottom. If I simplify this, I can write this as x plus 1 over x. So f of x is basically the x function, because as x's get very, very large, the 1 over x part becomes negligible. Now to make that argument a little more secure, observe that if I take f of x and move this x to the other side and I look at f of x minus x, and I take the limit as x goes to, well, either one of the infinities, then that's equal to this 1 over x limit as x goes to either one of the infinities, and that of course is 0. So as you go out far enough, the f of x function and the x function become virtually the same. In other words, the y equals x line is a different kind of asymptote for this function. Here is the picture to show you what this is. I won't go through all the details of generating it. But here is the y equals x line, and here is the graph of the function, which you can check on your own sometime. And you see, as you go far enough out in the two directions, this function gradually approaches the y equals x line. This is sometimes referred to as a slant asymptote, or sometimes it's called an oblique, if you like that word, asymptote. And that means it's a line that's not vertical or horizontal, that the curve is nevertheless approaching as x gets very large or very small. Does it have to be a line? No, it doesn't have to be a line. Here's an example where a curve is going to approach another curve. So let's take x cubed minus x squared minus 8 all over x minus 1. Now if you do a straightforward division, polynomial division, this becomes x squared minus 8 over x minus 1. And you can see we're in the same situation we were before, except now it's an x squared, and that's the curve this will approach. So let me give you the same argument. Observe if I take the limit as x approaches either direction of infinity, the original function here, g of x, and I bring the x squared to the other side, minus x squared, that's the limit of what's left here, which is the minus 8 over x minus 1. As x is approaching plus or minus infinity, of course, the x's grow large, this just becomes 0. So g of x and x squared are approaching each other as x gets very large in either direction. And so if we go ahead and look at the graph here, you'll see what's happening. This is a little more interesting. X squared, I'll dot that in as the asymptote here. So here is the curve y equals x squared, which is the asymptote. And this g of x also has a vertical asymptote at 1, so let me mark that here because it'll help me draw it. And here's what the graph of the curve g looks like. In the middle, it is asymptotic to this x equal 1 vertical line, but you see as we go farther out, here and here, it is approaching the y equals x squared line, or curve. So this is an example of an asymptote that is not a line. So be aware that this can happen with rational functions, and sometimes that can be very useful because in the end we could replace g of x by x squared to save ourselves some computational difficulty. Let's look at functions whose graphs have either vertical tangents or cusps. And remember what the idea is for this. Sometimes you have curves that look something like this, where at some point the tangent is vertical, and so the slope of that tangent would be infinite and therefore undefined, so the derivative doesn't exist there. Or you might have something like that absolute value function where the function's not defined at a corner, or sometimes it's at some sort of a cusp like this where it's not defined. So those are the sort of functions we want to look at here briefly. Let's start out with one that has a nice cusp in it, and it's sort of a classic function. Y equals x minus 4 to the 2/3 power. And what we want to do here is what we've been doing, and I'll just shorten it up. I'll just say find everything and produce a graph at the end. Okay, before I go any further with this, let me rewrite this so I can point out something. If I rewrite this and separate out the powers, I can rewrite it as x minus 4 squared to the 1/3 power. Now by doing that, the x minus 4 squared makes this greater than or equal to 0, and then the cube root rather, doesn't change that, so this is still greater than or equal to 0. So whatever this function is, it's at the x-axis or above it. It's also continuous everywhere. There's no place where this function breaks. That will be useful to know. All right, solution. Let's look for x-intercepts. I think everybody knows now that x-intercepts are where y is equal to 0. So I look at this and ask myself, when would this be 0? This would be 0 when x is equal to 4. So that's immediate. I can also now look at y-intercepts. And again, I hope you know that that means that's where x equals 0. And if x is 0, I have minus 4 squared, which is 16, cube root of that. So I have y is equal to 16 cube root. And let me just approximate that so I'll be able to look at the graph later and have a sense of where it is. That's about 2.5. Okay, let's look at vertical asymptotes. Vertical asymptotes. Well, this function's continuous everywhere, so it's not going to be undefined anywhere, certainly, and so it's not going to have any vertical asymptotes. It might have a horizontal asymptote. Let's at least check that out. Horizontal asymptotes are checked by taking the limit of the function which I guess I could leave in the second form, x minus 4 squared to the 1/3 power, and take that limit as x goes to plus or minus infinity, and ask myself what happens in here. Well, as the x in here gets very large, the minus 4 has no real effect. It's getting squared and very large, and then the cube root of a very large number is large. So what happens in the end is that this heads off to infinity. Since this is not going to a real number, there are no horizontal asymptotes. So there are none of those either. Well, that's interesting, and certainly makes this easier to look at. These two don't exist. Let's continue on. The next thing we want to look at is our first derivative. That will be the derivative with respect to x of x minus 4 to the 2/3 power. I think this form's a little easier for taking the derivative. That's going to be 2/3 x minus 4 to the minus 1/3 power. And whenever you have negative powers, this is just algebraic advice, you should probably rewrite this so it's a fraction. It's easier to make judgments if you have 2 over 3 times x minus 4 to the 1/3 power. Notice that this is never 0. A fraction can only be 0 if the top is 0, and this can't happen. It also doesn't exist for x equal 4. That would make the bottom 0. So that's worth noting. Let us now look at the second derivative as we build up our toolkit here. The second derivative, well, let's see, which form shall we take? I'm going to take this form, because if you look at this last form, you might say to yourself, well, this is a quotient, perhaps I should use the quotient rule. But it's a quotient where the top is a constant. And if the top or the bottom of a quotient is a constant, you shouldn't use the quotient rule. It's easier to use something else. In this case, I'm going to use this form here and then just use my power and product rules. So I have 2/3 x minus 4 to the minus 1/3. And let's just go ahead and run that through the 2/3 stays, minus 1/3 here, x minus 4 to the minus 1/3 minus 1, so that's minus 4/3 times the derivative of the inside, which is just 1. If I then simplify this, I'm going to get minus 2 over 9, x minus 4 to the 4/3 power. Notice that this is always negative, because the bottom is always positive, and there's a negative sign on the top. And the bottom is always positive because of this 4th power. So if this is always negative, the second derivative is always negative, means that the original function y is concave down. Always. So I don't have to check that in my chart. I know that it is always concave down. That's handy. That turned out to be very nice. So I really only have to do the chart for this first part. So it's going to be a small chart. Let me just put it here. I have one number, the number 4. This was never equal to 0, so there's only one number 4 where this might have something interesting. And I'm only looking at the first derivative. So if I go below 4 to the left, and I can choose whatever form is most easy to look at. If I choose choose a number below 4, I could choose 0, for example. This would be negative, so the whole thing would be negative. That means the original function is decreasing, going downward. If I then choose a very large positive number, something above 4, this will always be positive. So this means the original function is increasing. And from here I see that I must have here a local minimum. So this turned out to be a fairly easy function. Let's finally look at the graph and see what we've got here. Now I said this was a function with a cusp, and indeed it is. And you'll see that cusp coming right up. 1, 2, 3, 4. Here is where it had an x-intercept. It has a y-intercept up here between 2 and 3. Let's just mark it there. And if you graph it, it's concave down here and concave down on the other side. And this point here is sometimes referred to as a cusp, a point that is a corner on the graph of some kind where the derivative is not going to exist for some reason or other. And in this case, it's because of the division. When we do the derivative, the x minus 4 ends up on the bottom, and so we can't divide by 0 at 4. That's why there's no derivative there. So there's an example of what you can do with a function that has a cusp. For other kinds of functions, you might have a tangent that is vertical. Let's look at one of those here. 6x to the 1/3 plus 3x to the 4/3. And we want to find everything again and graph it. This one, again, I can simplify it, so I'm going to pull out 3x to the 1/3 I see times 2 plus x. This is also another one of those functions that's continuous everywhere, so it's defined everywhere, has no holes. And then we can quickly run through the process here. Check intercepts. The x-intercepts, that's where y is equal to 0. When would this be equal to 0? Well, when x is 0 or x is minus 2. Y-intercepts, that would be where x is 0. Putting x equals 0 in here, I get y equals 0, so that's easy. There are no asymptotes, or I should say no vertical or horizontal asymptotes. That's easy to see by checking the limit for the horizontal, and of course the function's always defined, so no vertical. The second thing that we need to do here is to find the derivatives. So the derivative of 6x to the 1/3 plus 3x to the 4/3. First derivative of that, well, that's easy enough. The powers are going to come down. This simplifies out very nicely. I'm going to take the bold step of skipping the steps here to show you what it looks like in the end. It will be 2 times 1 plus 2x all over x to the 2/3 power. Now remember to simplify things, and if you get negative powers, be sure to write them as fractions and then combine into a single power. Here's what you get in the end. This, now we can ask the question, when is this 0? It's 0 for the top being 0, which is when x is equal to minus 1/2. And it doesn't exist whenever the bottom becomes 0, which is when x is 0. So it doesn't exist for x equals 0. All right, that's the first derivative. The second derivative is when I take the derivative of this expression here, 2 times 1 plus 2x over x to the 2/3. If I then work that out and simplify it again, I'm going to leave out the steps. You can check that on your own. What you should end up with is 4/3 times x minus 1 over x to the 5/3 power. Now this expression here is 0 for whenever the top is 0, which is going to be when x is equal to 1. And again, I'll just mark it here. This doesn't exist for x equals 0 either. Okay, now it's time for a chart. So our first derivative, 2 times 1 plus 2x over x to the 2/3. And notice that the bottom here is always positive, so that will not affect the plus or minus sign of the first derivative. The second derivative is 4/3 x minus 1 over x to the 5/3. And because this is the fifth power here, this will be affected by negative signs, so we can't learn anything from that. The 3 points that turned up to be of interest were minus 1/2, 0, and 1. For the first derivative, it was minus 1/2 and 0 that mattered, so I'll just go ahead and mark these like this. And then for the second derivative, it was 1 and 0, so the 0 continues, and then the 1 comes into play. Once again, as we've done before, if I go below minus 1/2 to minus a million, say, the bottom's positive, so I could ignore that. This becomes negative. So the first derivative is negative. Y is decreasing, hence going downward. Between minus 1/2 and 0, I can pick a number, and I will find out very easily, like minus 1/4, that this is going to be positive. So y is increasing, the original function, and hence going up. And for numbers above 0, positive numbers of any stripe, this is going to be positive. So the first derivative is positive. The function is increasing from 0 on to the right. Now notice, of course, that the function does not exist here at 0, or the first derivative at least does not exist there. Let me write that down. Y prime doesn't exist on this line where x is equal to 0. I also notice that I have a decreasing and an increasing right next to each other going from left to right. That means I automatically have a local minimum. Okay, on this line, let's look at the second derivative. Here's the second derivative. If I pick a number that's below 0, negative, this is negative on the top, negative on the bottom. That makes the second derivative positive. So y is concave up, and hence looks something like that. Between 0 and 1, I can pick a number like 1/2. This will be negative here and positive here. That makes the second derivative negative. Y is concave down. So it looks something like this. And then if we choose a very large positive number, this will be positive. So the second derivative is positive. Y is concave up, and looks something like this. And for inflection points, both of these points lie on the curve, and so these are both inflection points. Now don't confuse yourself. I said that the derivative doesn't exist here, and that's true, but the original function does exist at 0. So this is perfectly good point on the curve, and so there are in fact 2 inflection points. Finally, we can produce a graph using all of that information. Y equals 6x to the 1/3 plus 3x to the 4/3 is our original function, and you can see it is defined for 0, as I mentioned. To get a couple of points here that I need to mark, I know that the x-intercepts, I know that when x is 0, y is 0. I also know when x is minus 2, y is 0. Those are things we worked out before. If x is minus 1/2 or x is 1, I didn't know what the y value was, so I needed to calculate it. So put those numbers in here. Putting the 1 in is easy. You just get 9. Putting the minus 1/2 in, if you simplify it, you get approximately minus 3.6. That'll just give us a little something to judge where points ought to be on this curve. Now this curve is a little strange looking compared to ones we've seen before. So let's go ahead and see what we've got here. We mark 9 about here. That's roughly correct. There's 1. There's minus 1. Down here I'll have a minus 4. And over here the minus 2. This curve is going to come down here like this and pass through minus 2. It will have a curve upwards passing through 0 and be tangent here. It will have a concave down part over here to 1, and then it switches to concave up at this point 1, 9. So there's this point here, which was our local minimum, which we saw on the previous page. This is one of the 2 inflection points. Here at 0, we actually have a vertical tangent, which is the reason that this is the function we're looking at right now. And so we have concave up, and then concave down and concave up again. This is a vertical tangent. It is also, of course, an inflection point. But vertical tangent means that there's no derivative at this point, and that's the reason we were doing this curve at this time. So there's a couple more examples to add to your collection of what curves look like. Some exercises for you to try. Let's look at this function. Y equal x squared over 1 minus x cubed. As we've been doing, you want to find everything about this. So let me make the list. You want to find y-intercepts. You want to find, x-intercepts. You want to find also y-intercepts. You want to find where it is vertical, where it has vertical or horizontal asymptotes, where it is increasing or decreasing, where it has local maxes or mins, concavity, whether it's concave up or concave down, where it has any inflection points, and finally you want to produce a graph of this. Now this function is unassuming, this x squared over 1 minus x cubed, but it'll take you a bit of work to get through this. So give it the appropriate amount of time and then come back and, well, let's just see how this worked out. Here is the function, rational function x squared over 1 minus x cubed. Let's go down the list. We're looking for y-intercepts. As you know, that's where y, or x-intercepts, that's where y equals 0. And that's only going to happen when x is 0. If we're looking for y-intercepts, That's where x is 0, so we put x equals 0 in here, and we get y equals 0. If we look for vertical asymptotes, as we learn to abbreviate more and more, vertical asymptotes will happen when the bottom goes to 0, and that only happens for x equal 1. So we have one vertical asymptote. The horizontal asymptotes, in this case, it's probably worthwhile to look at what happens as you go in the two directions separately. The limit as x goes to minus infinity of this function. The top remains positive always because it's squared. And the bottom, notice that as I go to negative infinity, the x cubed remains negative, so with the other negative, this becomes positive. So in the end, because it's squared on the top and cubed on the bottom, this will go to 0, but it will go to 0 from above, from the positive side. And if you take the limit as x goes to infinity, positive infinity, of the same function, you will see that you get 0 again. But this time, because the x is getting very, very large and positive, this negative remains. This becomes negative. So you're approaching 0 from below. Now, in either one of these cases, the horizontal asymptote is y equals 0, the x-axis. But from above and from below will help us in drawing the graph later, and I'll point that out when we get to that. Now let's go on to finding the derivative, the first derivative, that is. So this is the first derivative of x squared over 1 minus x cubed. Well, that requires the quotient rule. So let's walk that through once again. 1 minus x cubed has to be squared on the bottom. It starts out the top, 1 minus x cubed, times the derivative of the top, which is 2x, minus the top x squared, times the derivative of the bottom, which is minus 3x squared. If you then simplify this, you get x times x cubed plus 2 all over 1 minus x cubed squared. This will be 0 for whenever the top becomes 0. That'll certainly be true when x is equal to 0 here. And in here it'll be true when you have minus the cube root of 2. Now for later use, let me approximate that. That's about minus 1.25, so I can keep track of that. Also, I observe that, as I noticed before, this doesn't exist, as indeed the function originally doesn't exist for x equal 1, because that's division by 0. We need the second derivative, so let's take a quick look at it. The second derivative is the derivative of the first derivative, which is that x times x cubed plus 2 all over 1 minus x cubed squared. That was the first derivative. If we then walk this through, and I won't walk through all the details here, I'll assume that you can do the quotient rule yet again. What you end up with is 2 times x to the 6th plus 7x cubed plus 2 all over 1 minus x cubed cubed. This expression will become 0 for, and if you use the quadratic formula in here, you will find that this is for x is equal to the cube root of minus 7 plus or minus the square root of 41 all over 2, all of which reduces upon approximation to approximately minus 1.9 or minus 0.67. And that's all we'll need when we're doing our chart to know roughly where these numbers are. And again, this doesn't exist for x equal 1. So let's go ahead and look at the chart now that we have the two derivatives finished. And all of this is easier when you're doing this on your own paper because you have everything laid out in front of you. You can pull all the details together. So here is the first derivative repeated. And of course, remember the denominator of the first derivative is always positive. That will help us. The second derivative is that 2 times x to the 6th plus 7x cubed plus 2 number all over 1 minus x cubed cubed. So there's no necessarily positive number on the bottom here. In this chart, I have the following. Here I have approximately minus 1.9. That was a number of interest. The next one's approximately minus 1.25, another number of interest. Then approximately 0.67. then there was 0, and finally there was 1. So those were all the regions that we needed to look at. For the first derivative, it was this cube root of 2, negative cube root of 2 that we were interested in, and 0. So those are the two markers there. And remember, it wasn't defined at 1, so that's going to affect both the first and the second derivative. So I'll bring that 1 right on down. Then for the second derivative, it was these other two numbers. And so now we're set up to build our chart. As we've done before, if I come down here below minus 1.25, take a very large negative number, I have y prime greater than 0, y is increasing, so the function is going up. Between minus 1.25 and 0, I have y prime, you can check it here, is going to be less than 0. So y is decreasing, hence going down. Between 0 and 1, pick a number that's easy, like a half, and put it in here. You see that y prime is greater than 0, so y is increasing, hence going up. And finally, if you go above 1, you'll see that y prime is again greater than 0, and so the function is increasing and going up. Between at 0, we see that we're decreasing on the left, increasing on the right, so that gives us a local minimum. That's the first observation. And over here at that minus cube root of 2, we have increasing and then decreasing, which gives us a local maximum. All of this is easy to read off of this chart. Down here, we look for what the second derivative will tell us. If we're below this minus 1.9, we can check this out. The second derivative is greater than 0. So y is going to be concave up and look something like that. Between minus 1.9 and 0.67 is our favorite number. And let's see, I should have minus 0.67 up here, sorry. Then that's going to be minus 1 would be a nice number to choose. You put that up here, you'll see that the second derivative is less than 0. So y is concave down. And then over here, y double prime will be greater than 0. If we are in this region here, we can choose 0 as our number. We put 0 in here, this becomes positive. So y is concave up. And then finally, y double prime is going to be concave down. So the concavity does change as we cross this point here where the function is not defined. So concave down, y is concave down. And so there are our reasons. Here we have a vertical asymptote, so again there's no inflection point even though it's up here and then down here in concavity. This is concave down here. So these 2 points, which are on the curve, are in fact inflection points. So those are okay as far as that goes. Now we're ready to draw the graph. And if you have this chart, you can set it aside and keep it in front of you. X squared over 1 minus x cubed. And here's the graph that I came up with, which reflects all the information we just saw. Let's see here. At 1, we have a vertical asymptote where the function is not defined. It's going to go up like this on the right-hand side. The left-hand side looks something like this, where, let's see, we have at this point here a local max. At this point here, which was our minus 0.67 roughly, approximately, that is going to be an inflection point. And then we had another one over here, which was at approximately minus 1.9. So these 2 points here are inflection points. This was a local max here. This, of course, is a local min at 0. And this was the horizontal asymptote, which is the y equals 0 line that we said we'd approach. And notice that we are coming from below to the right, and we are coming from above down to that asymptote on the left. And that's what we predicted earlier. So that should be more or less what you ended up with on your first exercise here. Let's look at a simpler one as our second one. Y equals x plus the sine of x. Again, find everything, and I won't list it out this time. I think you must have that memorized by now. But we want to find everything on one period of the sine function. So we'll pick the period 0 to 2 pi just to make it the same for everyone. So give that one a try. This one's computationally a little easier, but probably tests your knowledge of the sine and cosine functions a bit. Here is the beginning. Again, we'll look for x-intercepts first. Now, x-intercepts are where y is equal to 0. When will x plus sine x, which is y, equal 0? Well, I claim it will only happen when x equals 0. Certainly when x is 0, these will both be 0. One way to see is to say, well, if y is 0, then I'm asking sine x, and put the x on the other side, I'm asking when is sine x equal to minus x? And you can do a quick little graph for yourself to see that. Here is the minus x curve, this 45-degree line going off in the reverse direction. And if you remember, the sine curve goes like this. The only place where they intersect is there at 0. So that is the only place where there's an x-intercept for this function. That's a quick way to see that. Y-intercepts, that would be where x is 0. When x is 0 here, of course, y is 0. So that's easy. This is a combination of a linear function and a trigonometric function. The sine function, which is defined everywhere, this is all continuous everywhere, has no asymptotes of any kind. No horizontal or vertical asymptotes. Now let's go on to the derivatives. The first derivative of x plus sine x, also an easy derivative. 1 plus cosine x is what we get. We want to know when this is 0. So this is 0 for whenever 1 plus cosine x equals 0, which means cosine x equals minus 1. Now remember where we are. We're on this interval from 0 to 2 pi. So if we draw a quick picture here to remind ourselves of what's going on, we want to know where the cosine is going to be minus 1. If we look at the picture here and remember the cosine function looks something like this. Here is 2 pi, here is 0. At what point does the function cosine become the height of minus 1? Well, it happens exactly once, here at pi. So for cosine x equal minus 1 only happens when x is equal to pi. Finally, the second derivative is the derivative of the first derivative, and the derivative of 1 is 0. The derivative of cosine is minus sine x. When will this be 0? This will be 0 for, well, when sine x is equal to 0. And where is the sine equal to 0 in the interval from 0 to 2 pi? Well, we already have a sine function up here. Let me just complete it to 2 pi. It looks like it's 0, 1, 2, 3 times. So it's 0 for sine equals 0, for x equals 0, x equals pi, and x equals 2 pi, all the multiples of pi. So we're prepared now for our chart. Here is the first derivative, 1 plus cosine x. Here is the second derivative, minus sine x. Now remember, we are on an interval that stops. It goes from 0 to 2 pi, and so I'll mark this very solid line here and indicate there's nothing out here, see? The function is only defined in this interval. And then the numbers that we saw of interest were 0, 2 pi, and then pi. These are the only 3 numbers of interest. And that was of interest to both the first and the second derivative. So I have this little chart now. Nothing's going to happen outside here. And if I look for the first derivative between 0 and pi, I come up here and ask myself, what is happening to the first derivative as the angle x here goes between 0 and pi? So I'll draw my little trigonometric circle diagram to remind myself. The angles between 0 and pi are up here. Up here, the cosine varies itself from 1 all the way to minus 1. But if you add 1 to that, that means the cosine is going to vary between 0 and 2. And since that's the case, the first derivative above 0 and below pi is always positive. Y is increasing, and so this is going up. If we're over here between pi and 2 pi, my circular diagram says between the angle pi and 2 pi, I'd be down here. What happens to the sine? Well, the sine is always negative in these quadrants. Since there's a negative out front here, that means the second well, we're not at the second derivative. Sorry, we're still working on the first derivative. The cosine passes through the same values it did before, so it's going to have exactly the same result. The first derivative is greater than 0. Y is increasing and going up. And since I've already started this, let's look at the second derivative here, since we can look at this region. As the sign is always negative here with the negative, that means the second derivative is always positive in this region. So y is concave up. And then over here in this region, the second derivative here, when we have signs up here, they're all positive. So that means with this negative sign, the second derivative is negative. Y is concave down, and so it looks something like this. Since the function is defined everywhere, this point in the middle is indeed an inflection point. So we've learned everything we can about this function using all the parts that we've had to develop. We can now draw the graph of x plus sine x on the single interval or single period 0 to 2 pi. Well, pi was an important point, and if you notice, when x is equal to 0, pi, or 2 pi, the sine of x is 0. So that means the y value becomes the same thing, 0, pi, or 2 pi. So if I mark these points on the y-axis, 0, 0 is on the curve, pi, pi is on the curve, and 2 pi is on the curve. Then we learned that the function is concave down here and then concave up here. And that point in the middle is the inflection point, one and only inflection point. Now this is a picture of this function on one period. If we then extend it in both directions, we'll have the function in over infinitely many periods, and has the same shape in each one of them.